Welcome to the final video, your toolbox and roadmap. This is the final video. You have seen what these systems can do throughout 9 videos. So the only fair way to end is to answer the obvious question. How would you build one? This final chapter is different from other 9. There is no new theory, just a map. The tools you would actually reach for and one concrete project you can start today. The tools you would actually think of it as a toolbox we have been describing this whole series, finally laid out on the bench. So, everything begins with data, so begin with the tools to handle it. In this scenario, Python, that is pandas and numpy for tables and numbers, and xarray when your data has the shape of weather, read of values spread over space and time. But the real question is, where energy data even comes from? And here's the good news. Enormous amount of it is free and open. Eurogrid's data lives on the ENTSO-E transparency platform. In the United States, National Renewable Energy Laboratory publishes vast solar and wind datasets. Open-Meteo hands you weather for nothing. And pvlib, written by solar engineers, models exactly how much power a panel should produce. You can get real data and start today without asking anyone's permission. For the classical machine learning of chapter 2, the whole ecosystem is essentially 3 names. Scikit-learn for regression, trees, and clustering. Actually, Swiss Army knife of the field. And then XGBoost and LightGBM and gradient boost champions. Of course, they quietly win forecasting competition after competition. If you learn just one modeling tool this year, make it gradient boosted. That's what I'm recommending. It is astonishing how far it will carry you before you need anything fancier. You don't need bigger, larger models to kickstart. When you are ready for the deep learning of chapter 3, there are 2 great frameworks actually. PyTorch, which the research world has largely settled on, and TensorFlow with Keras. But for forecasting specifically, which remember is the killer application, which means you don't have to build anything from scratch. Libraries like Darts and the Nixtla suite hand you classical models, deep networks, and as well as some other libraries and honest probability forecast, all behind one clean interface. And the newest option of all, pre-trained time series foundation models like Chronos and TimesFM that you point straight at your data and gets a forecast with no training at all. So it is zero training. For the more specialized methods, it has its home network. Graph networks from chapter 6, PyTorch Geometric. Reinforcement learning from chapter 5, stable baseline tree with gymnasium. And crucially, energy-specific playgrounds already exist right now in labs and also in universities. Grid2Op for the transition grid, CityLearn for buildings. So you can train agents without a real grid to break. That's the good news. Physics-informed models from chapter 7, DeepXDE, and underneath all of it sit a category every power engineer should know. The open source grid simulators, pandapower, PyPSA, OpenDSS. Model a real network, run a power flow, generate the very data your models learn from. For an electrical engineer, this is home turf. This is your edge. That is a lot of names we have talked about, and so let me collapse the whole thing into one part. The single project I would actually start with: forecast electricity demand. Step 1, get real data. Load series from ENTSO-E, weather from Open-Meteo, and the calendar. Step 2, build a baseline with XGBoost and a few good features. This alone will be better than you expect, and it teaches you the shape of the problem. Step 3, level it up. Bring in darts or Nixtla. Try sequence model. And the part most people skip, make it probabilistic. Predict a range, not just a line actually. Step 4, evaluate honesty. Mean absolute error and the pinball loss, you have to measure it. Always on time you held back. Never on data it has already seen. And step 5, specialize toward whatever pulled you into this series. That's very important. The single path will teach you more than any course. This one included actually. And that brings us all the way back to where we began. 10 chapters ago, I asked you to picture one thing. Single needle holding at 50 Hz, the heartbeat of the grid. You remember, everything we have built since the workhorses and deep networks and the agents and the graphs and everything we have built. The forecast, the physics, every last piece is about keeping that needle steady. The grid is the largest, most complex machine humanity has ever built. For the first time, we have tools to understand it, predict it, and operate it, and we are living in the best era to start with AI, at a scale no human team ever could. That is not a hype actually, it is the next chapter of engineer's job. The tools are open, the data is free, the problems are real and waiting actually. So go build something, go help keep the needle steady. Thank you for watching the whole series. Let me meet you in another